Hello and welcome to another Let's Study video. The format of this video is that I will be reading and learning about a topic of which I don't know a whole lot about in this video, and hopefully some kind of distilled results of which can be recorded in this video for myself and others, such as whoever's listening to this, and it may prove helpful. So today's topic is going to be learning about the architecture of the processor I have in my computer. I have a Ryzen 7 1800X CPU or processor, and I want to write programs which might leverage its hardware or simply write around the limitations of the hardware without me, say, shooting myself in the foot with asking it to do something more precise than it's able to do. And so I studied assembly in college for a very brief period. I struggled with it, and but I knew its potential for understanding what's happening on the computer, and so I feel I need to learn a little bit more about that, at least to understand where it may become relevant or not, and also just to see what the world of being an architectural programmer or someone who cares about the architecture of the hardware they choose might look like. So if we learn something, we haven't wasted our time. So what I'm going to be reading is I'll just be starting with the AMD Architecture Programs Manual. It has the volumes 1 through 5, but of course with the volumes manual it will have an overview, and we're just going to cover that. Okay, so we're just looking over the contents. We have an overview of the architecture, which is something I want to learn. An overview is very important that we read. It's sort of exactly what we're looking for. I'm curious to know what it thinks this audience is, of who is reading such a document, and how it's organized. And so I understand what registers are, what instruction sets are, and I understand the difference between most instruction sets and most numerical representations as well as floating point representations. I understand a little bit about modes of operation, just a little bit, and I know some terminology and the organization of how memory on computers works, so it looks like we're going to learn a little bit more about that here. Okay. So general purpose programming is probably going to be our best bet for what we would end up doing. I believe. Okay, it doesn't show the other system programming. I think that's in 1, 2, 3, 4, 5, 6 chapters. What is this? Well, it's 1 through 5, but it has 6. I wonder what one's the extra. Probably this overview. No, I don't think so. So this is interesting. The specification that it's a scientific programming. So I wonder what that means for this. I'm curious about this matrix arithmetic operations, because matrices often have many points, well, many pieces of information. So like a 1x4 matrix has 4 pieces of data. I'm curious to see what kind of matrix mathematics are available as operations. I'm wondering if this feature detection here is with the DirectX 12 graphics API, you can detect what feature set is supported by any sort of display adapter. So I wonder if the AMD64 architecture has various features, and you can detect it based on the CPU that you're currently using. And so you can turn on or off certain features, or utilize certain features or fall back on older ones based on some feature list. Potentially that's what's going on here. So that ends about the content and about what I'm at least a bit interested in, and or have something or anything really to talk about, or just to say. I'm certainly out of my pond with this. I don't quite know where I am or what I am doing. At least understand the words, some of them. We'll learn more as we go. Okay. So about this book. This book is part of a multi-volume work entitled the AMD64 Architecture Programmer's Manual. This table lists each volume and its order number. So we have Volume 1 on Application Programming, Volume 2 on System Programming, Volume 3 on General Purpose and System Instructions, Volume 4 on 128-bit and 256-bit media instructions, and finally on Volume 5 on 64-bit media and the x87 floating point instructions. So the audience of this book, this volume is intended for programmers writing application programs, compilers, or assemblers. It assumes prior experience in microprocessor programming, although it does not assume prior experience with the legacy x86 or AMD64 microprocessor architecture. Okay. So, prior experience with the microprocessor programming, I don't think I have anything that gets there beyond writing and compiling. Well, not writing and compiling, but writing assembly code for a emulated microprocessor. So I did do emulation with microprocessor, and I can't even recall what program I used or what microprocessor I was emulating or which one we were using in class. But I believe we were working on a microprocessor of some kind, some emulation of a microprocessor, and we were writing assembly. Okay. This volume describes the AMD64 Architecture's resources, and functions that are accessible to application software, including memory, registers, instructions, operands, I/O facilities, and application software aspects of control transfers, including interrupts and exceptions, and performance optimization. So, we'll get to learn about the resources and the functions that is accessible to us writing applications, including the memory, the registers, instructions, operands, I/O facilities, and application software aspects of control transfers. So effectively, we're going to be able to learn what we have available for us on this hardware to write applications in terms of memory, where we can store these in registers, what instructions we have available to us, what operands we have, and the input-output facilities for our applications. So, and control transfers, which might be a topic not even approachable by me for a while. So, for some system programming topics, including the use of instructions running at a current privilege level, CPL of 0, most privilege, are described in Volume 2. Details about each instruction are described in Volumes 3, 4, and 5. Okay, so organization of this volumes. This volume begins with an overview of the architecture and its memory organization, and is followed by chapters that describe the 4 application programming models available in AMD64 architecture. So we have the general purpose programming. This model uses the integer general purpose registers, GPRs. The chapter describing it also describes the basic application environment for exceptions, control transfers, I/O, and memory optimization that applies to all other application programming models. We have streaming, SIMD in extensions, SSE, programming. This model uses the SSE registers and supports integer and floating point operations on vector or packed and scalar data types. So we have the YMM and XMM. Okay. But we have the multimedia extensions, MMX programming. This model uses the 64-bit MMX registers and supports integer and floating point operations on vector, packed, and scalar data types. And then we have the x87 floating point programming. This model uses the 80-bit x87 registers and supports floating point operations on scalar data types. The index at the end of this book, it functions like an index. So we have conventions and definitions. So let's see how many we know, or familiar to us. The following section, notational conventions, describe notational conventions used in this volume and in the remaining volumes of this manual. This is followed by a definitions section, which lists a number of terms used in the manual along with their technical definitions. Some of these definitions assume knowledge of the legacy x86 architecture. See related documents. Finally, the registers section lists the registers which are part of the application programming model. Okay, so we have notable conventions. We have hashtag GP0 in parentheses. This is an instruction exception. In this example, a general protection exception with error code of 0. Okay. We have 1011B, a binary value. In this example, a 4-bit value. Okay. So it looks like we have ones and zeros with a B at the end, representing that this is a binary value of 4 bits. We have a hexadecimal value here. F0EA underscore 0B0 to H. Underscore characters may be inserted to improve readability. Okay. That doesn't look remotely readable. But okay. We have 128. Numbers without an alpha suffix are decimal unless the context indicates otherwise. So 128 is a decimal 128.0. I'm confused. We have 7:4, a bit range from bit 7 to 4 inclusive. Okay, so it's bit 7 to 4, from bit 7 to 4, both containing 7 and the 4th bit as well, inclusive. The higher order bit is shown first. Commas may be inserted to indicate gaps. Okay. So we have CR0 to CR4, a register range. So this is from registers CR0 and CR4, and it's inclusive, so containing both 0 and 4. Low order register first. So this breaks the breaks sort of convention from above. We have a bit range that starts with the higher order bit shown first, and then we have a register with the lower order register first. So a little bit of direction difference. We have CR0 PE. It's notation for referring to a field within a register, in this case the PE field of the CR0 register. Okay, so this is similar like array notation in C. So within these brackets, we're notating a member, sort of like a location of the CR0 register. And it looks like we can do an array notation, or we could do it in a dot notation. I'm not sure if this is called an array notation, but that's why you see it most often. And I would definitely call this a dot notation. Okay. So we have register CR0, PE is set to 0, set to 1, equals 1. PE field of the CR0 register is set or contains the value of 1. We have EFER, EFER, with field LME equals 0. The LME field of the EFER register is cleared, or now contains this value of 0, or we're setting it to 0. Then we have DS:SI, a far pointer or logical address. The real address or segment descriptor specified by the segment register, DS in this example, is combined with the offset contained in the second register, SI in this example, to form a real or virtual address. Okay? We have R flags, 13 to 12, a field within a register identified by its bit range, for example, corresponding to the IOPL field. Doesn't say if this is inclusive or not, like the other ones have before. Okay, so those are conventions of notating things. So we learned how they in this document, not everywhere in the world, but we learned the notation conventions in this document. Binary values are represented with a B at the end, hexadecimals with an H at the end, numbers without a B or an H are decimal values. Bit ranges are represented by a integer with a higher order bit shown first. Register ranges are shown with a dash from lowest to highest. Notation for referring a field within our registers is using array or dot notation. The setting of a field or a register is using an equal sign. And pointers are separated by real and offset with a colon. And a field within a register may be referenced using its bit range. So the bits 13 to 12 of R flags is being represented here with this convention. I feel like we learned a little bit, so at least we'll be able to read later on. I feel like I understand at least the conventions, not necessarily what they're actually representing. So I don't know what the fields of registers are. I imagine registers as simple buckets of information for information to be stored in. I know that fields are most likely now. My idea of a field now is being adjusted, and I think it means that the field is a specified bit range within the register's total bits that is, used specifically for something, such as storing like an operator or a flag of some kind. So moving on to the definitions, we have 128-bit media instructions. These are instructions that operate on various 128-bit vector data types, supported within both the legacy SSE and extended SSE instruction sets. So SSE, what was that? Streaming SIMD extensions programming, SSE. Streaming SIMD extensions. And then we have 256-bit media instructions. These are instructions that operate on various 256-bit vector data types and supported within the extended SSE instruction set. So I wonder if, just judging immediately from this, we have a 256-bit media instructions. Now, does that mean that the largest integer bit that we can represent on a single operation on the AMD64 architecture is going to be a 256-bit integer all at once? Or is that going to be reduced by needing to use some of those bits for other things, such as an operator or a memory location? I guess those are what operands are. So I guess we're going to find out soon. So we can figure out and we can learn, perhaps even today, like what is the largest integer number we can express on the CPU at a given moment, or a cycle on the CPU at one time. Now I know that there's going to be methods of splitting up like an integer into several locations, and we can build like the biggest integer possible. But just as it is, it'll be interesting to know. Here we have 64-bit media instructions. These instructions that operate on the 64-bit vector data types. These are primarily a combination of the MMX and the FreeDNow instruction sets and their extensions, with some additional instructions from the SSE1 and SSE2 instruction sets. So we have a lot of SSEs. We have SSE, Legacy, Extended SSE, and SSE1 and SSE2. So we have many instruction sets. This is a little confusing. We have many instruction sets. Now this probably, isn't the instruction set list that I was given when I was working with the emulated microprocessor, in which case my instruction set was like 30 of different operands, I think. Now I wish I had my notes. I don't think I even want to bother looking for them. I don't think they exist. Shame on me for not taking better care of the data and the notes I took in class, if I even took them. Okay. Where were we? Well, we were here at 64-bit media instructions. And then we just finished that. So we have the 16-bit mode. So we have modes. This is a 16-bit mode is a legacy mode or compatibility mode in which a 16-bit address size is active. And it's referring us to, or it's telling us to see the legacy mode and compatibility mode. We have a 32-bit mode, which is a legacy mode or compatibility mode in which takes a 32-bit address size is active. And then we finally have a 64-bit mode, a submode of long mode. In 64-bit mode, the default address size is 64 bits, and new features such as register extensions are supported for system and application software. And then we have this definition of absolute, which is said of a displacement that references the base of a code segment rather than an instruction pointer, in contrast with relative. Okay. AES, Advanced Encryption Standard, Algorithm Acceleration Instructions. It is a part of the streaming SIMD extensions, so the SSE. We have ACID, ASID, which is the address space identifier. We have AVX, which is extension of the SSE instruction set, supporting 128 and 256-bit vector packed operands. And we have AVX2, an extension of the AVX instruction subset that adds more support for 256-bit vector, mostly packed integer. Okay, well, wait a minute, this might be the answer to our question. Extension of the AVX instruction subset that adds more support for a 256-bit vector, and in parentheses it's called a mostly packed integer. Now, what is a mostly packed integer? Operands and a few SMD instructions. See streaming SIMD extensions. Then we have a biased exponent, the sum of a floating point values exponent and a constant bias for a particular floating data point type. The bias makes the range of the biased exponent always positive, which allows reciprocation without overflow. And we have a byte, which is 8 bits. I cannot tell you how many times, and it's embarrassing even in my own head, that I keep thinking a byte is 4 bits. A byte, 8 bits. 8 teeth in a big byte. I don't know. That'll be my mnemonic for remembering what a byte is. Okay, the definition of clear: to write a bit value of 0. We have compatibility mode, which is a sub-mode of long mode. In compatibility mode, the default address size is 32 bits, and legacy 16-bit, and 32-bit applications run without modification. And commit: to irreversibly write, in program order, an instruction's result to software visible storage, such as a register, including flags, the data cache, and internal write buffer or memory. We have the CPL, the current privilege level. And we have direct, referencing a memory location whose address is included in the instruction syntax as an immediate operand. The address may be an absolute or relative address. Compare indirect. Then we have dirty data, which is data held in the processor's caches. A cache? How would you say caches? I guess it's caches. Or internal buffers that is more recent than the copy held in main memory. Huh? How would that data be dirty? In my mind, dirty data is data that is now old. But this data, being called dirty, is held in the caches and internal buffers that is more recent than the copy held in main memory. So that confuses me, because new data is always good data. Old data could be bad data. That is flying in direct opposition of my intuition about what I would call dirty data versus not. Okay, we have displacement, which is a signed value that is added to the base of a segment in absolute addressing, or an instruction pointer for relative addressing, same as offset. We have double word, which is 2 words, or 4 bytes, or 32 bits. We have double quad word, which is 8 words, or 16 bytes, or 128 bits, also called octword. We have effect address size, which is the address size for the current instruction after accounting for the default address size and any address size override prefix. And then we have the effective operand size, which is the operand size for the current instruction after accounting for the default operand size and any operand size override prefix. And we have element, well, just referencing us to go see the vector definition. Okay, we have the definition of an exception. An abnormal condition that occurs as a result of executing an instruction. The processor's response to an exception depends on the type of execution. For all exceptions except SSE, floating point exceptions, and x87 floating point exceptions, control is transferred to the handler or service routine for that exception, as defined by the exceptions vector. For floating point exceptions defined by the IEEE 754 standard, they are both masked and unmasked responses. When unmasked, the exception handler is called, and when masked, a default response is provided instead of calling the handler. So we have extended SSE, which is a enhanced set of SMD instructions supporting 256-bit vector data types and allowing the specification of up to 4 operands. A subset of streaming SIMD extensions, SSE, includes the AVX, AVX2, FMA, FMA4, and XOP instructions. Compare it to the legacy SSE. And we have flush, which is an often ambiguous term meaning 1, either to write back if modified and invalidate, as in flush the cache line, or 2, to invalidate, as in flush the pipeline, or 3, change a value, as in flush to 0. So I know this word being used in graphics programming for flushing the command queue. So in which case we sort of, I'm not sure about invalidating or changing the value to 0, but effectively we flush the line by just waiting for things to end and waiting until it's done. So instead of flushing the command queue, we're just waiting for command queue to empty. So I guess, we're using it in a different sense. It's not even one of these 3 different meanings. So FMA4, we have a fused multiply add 4 operand, part of the extended SSE instruction set. We have FMA, which is a fused multiply add, part of the extended SSE instruction set. So I'm wondering if this multiply add is, well, somewhat of the operands that you would do where you're multiplying by a number and then adding it to one of your operands. So I wonder what this fuse multiply add is doing. I'm a little curious about that. We have the GDT, which is the global descriptor table, and GIF, the global interrupt flag, the IDT, the interrupt descriptor table. We have IGN, which is ignored, or the value written in is ignored by hardware. Value returned on a read is indeterminate. See reserved. We have indirect, referencing a memory location whose address is in a register or other memory location. The address may be an absolute or relative address. We have IRB, the virtual 8086 mode interrupt redirection bitmap. We have IST, the long mode interrupt stack table, and IVT, the real address mode interrupt vector table, and LDT, the local descriptor table. So it looks like we have a local and a global and an interrupt. So I'm not sure what these descriptor tables are, but they're here. Yeah, then we have Legacy x86. The Legacy x86 architecture, see related documents on page XXX. So XXX, that'd be what, 30? Page 30 of our prefix. I don't know my Roman numerals very well, but I'm imagining that's page 30 of the preface. 4 descriptions of the Legacy x86 architecture. We have the legacy mode, which is an operating mode of the AMD64 architecture in which existing 16-bit and 32-bit applications and operating systems run without modification. A processor implementation of the AMD64 architecture can run in either long mode or legacy mode. Legacy mode has 3 submodes: real mode, protected mode, and virtual 8086 mode. Now I'm curious about this virtual 8086. I don't know if I'm right or wrong, but isn't the 8086 some famous microprocessor out there? And is this virtual 8086 an emulation of it, of sorts? It's a virtual version of that chip. I'm curious to know if that is a feature of this architecture to be able to run 8086 programs. I guess we'll learn more. We have Legacy SSE, a subset of the streaming SIMD extensions, the SSE, composed of SSE 1, 2, 3, E3, E4.1, E4.2, and E4A instruction sets. Compare this to the extended SSE. We have LIP, LIP, which is the linear instruction pointer. The linear instruction pointer is equal to the base of a register plus some value, RIP. Because we haven't gotten to RIP yet. Okay. We have long mode, an operating mode unique. Ooh, this is interesting. Unique to the AMD64 architecture, a processor implementation of the AMD64 architecture that can run either in long mode or legacy mode. Long mode has 2 sub-modes, 64-bit mode and compatibility mode. Okay, here we go. We have LSB, meaning the least significant bit. LS capital B, LS also capital, is the least significant byte. We have main memory, which is the physical memory, such as RAM, and ROM, but not cache memory, that is installed in a particular computer system. We have mask, which is a control bit that prevents the occurrence of a floating point exception from invoking an exception handling routine, or a field of bits used for control purpose. We have the acronym AMB0, MB0, which is must be 0. If software attempts to set MBZ to 1, a general protection exception GP occurs. See reserved. We have memory, unless otherwise specified, is referring to main memory. We have MSB, which is the most significant bit, and then we have capitals MSB, which is the most significant byte. We have multimedia instructions, those instructions that operate simultaneously on multiple elements within a vector data type, comprises the 256-bit media instructions and the 128-bit media instructions and 64-bit media instructions. We have octword, which is the same of a double quad word, oct meaning 8. We have offset, which is the same as displacement. We have, overflow, which is an interesting topic I want to learn about. Overflow is defined as the condition in which a floating point number is larger in magnitude than the largest finite positive or negative number that can be represented in the data type format being used. We have the term packed, which we're just being referenced to see the vector definition. We have PAE, which is the physical address extensions. We have physical memory, which is actual memory consisting of main memory and cache. We have probe, a check for an address in a processor's caches or internal buffers. External probes originate outside the processor, and internal probes originate within the processor. We have procedure stack, portion of a stack segment in memory that is used to link procedures, also known as a program stack. In which case we have program stack here, referencing what we just read. We have protected mode, which is a sub-mode of legacy mode. We have a quad word, which is 4 words, or 8 bytes, or 64 bits. We have RAS, or a Z, read as 0. The value returned on a read is always 0, regardless of what was previously written. We have real address mode, which would be in reference to real mode, in which case is right here. Real mode is a short name of real address mode, a submode of legacy mode. We have relative, which is referencing with a displacement, also called offset, from an instruction pointer rather than the base of a code segment, contrast with absolute. We have reserved, which fields marked as reserved may be used at some future time. To preserve compatibility with future processors, reserved fields require special handling when read or written by software. Software must not depend on the state of a reserved field unless qualified or as a RAS, nor upon the ability of such fields to return a previously written state. If a field is marked reserved without qualification, software must not change the state of that field. It must reload that field with the same value returned from the prior read. Reserved fields may be qualified as IGN, MBZ, RAZ, and SBZ. So, MBZ is must be 0. RAZ is read as 0. Now I can't remember what IGN and SBZ were. So we will go back. MBZ must be 0, correct. IGN ignored. Okay. Now what's SBZ? Should be 0 down here. Should be 0. An attempt by software to set SBZ bit to 1 results in undefined behavior. Okay. We have scalar, an atomic value existing independent of any specification of location, direction, etc., as opposed to vectors. Set, to write a bit value of 1. Okay. We have shadow stack. A shadow stack is a separate protected stack that is conceptually parallel to the procedure stack and used only by the shadow stack feature. We have SIB, a byte, following an instruction opcode that specifies address calculation based on scale S, index I, and base B. We have SIMD, which is defined by single instruction multi-data, C vector. And we have streaming SIMD extensions, SSE. Here we go. These are instructions that operate on scalar or vector packed integer and floating point numbers. The SSE instruction set comprises the legacy SSE and extended SSE instruction sets. We have SSE1, which is the original SSE instruction set, includes instructions that operate on vector operands in both the MMX and XMM registers. If we have SSE2, this is defined as extensions to the SSE instruction set. And we have SSE3, which is further extensions to the SSE instruction set. Now we have SSSE3, which is even further instructions to the SSE instruction set. And then we have SSE 4.1, which is even further extensions. Okay, so SSE more stuff is just more stuff. Got it. And we have SSE-A, a minor extension to the SSE instruction set, adding the instructions X star Q, insert Q, move NTSS, and move NTSD. I'm interested to understand what those are. Here we go. We have a sticky bit. A bit that is set or cleared by hardware, and that remains in that state until explicitly changed by software. Interesting. And we have top. The x87 top of stack pointer. Okay. And we have TSS, the task state segment. And then we have underflow, which the condition in which a floating point number is smaller in magnitude than the smallest non-zero positive or negative number that can be represented in the data type format being used. Finally, we got to vector, which has two definitions. The first is a set of integer or floating point values, called elements, that are packed into a single operand. Most of the media instructions support vectors as operands. Vectors are also called packed, or SIMD, single instruction multi-data operands. Packed operands, okay? So a packed integer would be several integers, each being elements put together to form a single operand. Interesting. And then the second definition of vector is an index into an interrupt descriptor table used to access exception handlers. And then we have vex, which is vexing. Okay, vex. An instruction encoding escape prefix that opens a new extended instruction encoding space, which specifies a 64-bit operand size and provides access to additional registers. Interesting. Okay, and then we have virtual 8086 mode, which is a submode of legacy mode. And we have VMCB, which is a virtual machine control block. And we have VMM, which is a virtual machine monitor. And we have a word, which is 2 bytes or 16 bits. And we have XOP instructions, which are part of the extended SSE instruction set using the XOP prefix. Interesting. And then we have the XOP prefix, which is the extended instruction identifier prefix used by XOP instructions, allowing the specification of up to 4 operands and 128 or 256-bit operand widths. Okay, that concludes our definitions. And finally, hopefully finally, we have something here. We have registers. In the following list of registers, the names are used to refer to a given register or to the contents of that register. Okay? So we have AH-DH, the high bit of AH, BH, CH, and DH registers. Okay. High bit. So 8-bit, like D word, double word. So a word is, what's a word? Did we not learn that? Word. Quad word, 4 words, 8 bytes, 1 byte. 1 byte is 8 teeth. 8 bits. 8 bits, so 1 word. So, okay, that's interesting. So high, H. And then we have L for the low 8-bit of AL, BL, CL, and DL registers. We have AL-R15B, which is a low 8-bit AL, BL, CL, DL, SIL, DIL, BPL, SPL, and R8B to R8B to R15B registers available in the 64-bit mode. Okay. We have BP, which is the base pointer register. We have CRN, which is the control register number N. CS, which is the code segment register. We have EAX-ESP, which is the 16-bit AX, BX, CX, DX, DI, SI, BP, and SP registers, or the 32-bit EAX, EBX, ECX, EDX, EDI, ESI, EBP, and ESP registers. Comparing it to the RAX-RSP, which we'll get to apparently. EFER, which is the extended features enable register. We have E flags, which is 16-bit or 32-bit flag registers. And we have E flags, which is 32-bit extended flag registers, or flags register. We have EIP, which is 16-bit or 32-bit instruction pointer register. IP instruction point. EIP, which is a 32-bit extended instruction point register. So there's a commonality around where lowercase is, smaller. Uppercase is larger, meaning more bits to bytes. We have flags, which is a 16-bit flag register. GDTR, which is the Global Descriptor Table Register. And we have GPRs. I imagine we're going to be reading a lot about these. These are general purpose registers for the 16-bit data size. They are AX, BX, CX, DX, DI, SI, BP, and SP. For the 32-bit data size, they are EAX, EBX, ECX, EDX, EDI, ESI, EBP, and ESP. For the 64-bit data size, these include RAX, RBX, RCX, RDX, RDI, RSI, RBP, RSP, and R8-R15. Interesting. So the 32-bit data sizes and the 64-bit data sizes they look very similar, but instead of with an E, they are started with an R. So we have no prefix, AX, BX, CX, and then we have the E prefix, EAX, EBX, ECX, and then we have the R prefix, which is the RAX, RBX, RCX. Then we have the IDTR, which is the Interrupt Descriptor Table Register, and IP, which is the 16-bit Instruction Pointer Register. We have LDTR, which is the Local Descriptor Table Register, and MSR, Model Specific Register. We have R8-R15, the 8-bit R8B to R15B registers, or the 16-bit R8W to R15W registers. or the 32-bit R8D-R15D registers, or the 64-bit R8-R15 registers. We have RAX to RSP, the 16-bit AX, BX, CX, DX, DI, SI, BP, and SP registers, or the 32-bit equivalents and 64-bit equivalents, replacing the placeholder R with nothing for 16-bit size, E for 32-bit size, and R for 64-bit size. Okay, so here we go. Placeholders in front. Interesting. The R being used, possibly elsewhere in the book, which I then can't find an example of, such as here, is a placeholder for either nothing, E, or R. Interesting. We have RAX, RAX, which is the 64-bit version of the EAX register. We have RBP, which is the 64-bit version of the EBP register. RBX, which is the 64-bit version of the EBX register. We have ECX, which is the 64-bit version of the ECX register. We have RDI, which is the 64-bit version of the EDI register. We have RDX, which is simply the 64-bit version of the EDX register. We have R flags, 16-bit, 32-bit, or 64-bit registers. So that R is a placeholder for nothing for 16-bit, E for 32-bit, and R for 64-bit flag register. So R flags would be the 64-bit flags register. Just as right here. Okay, look, R flags, I was right. So the scheme follows. We're learning something. So we have capital R flags, which is 64-bit flag register. And compare the R flags, which we just read. Okay, we have lowercase RIP, which is 16-bit, 32-bit, or 64-bit instruction pointer registers. Register. RIP, the 64-bit instruction pointer register described above. Now RSI. Well, it's the 64-bit version of the ESI register. RSP, which is the 64-bit version of the ESP register. And we have SP, which is the stack pointer register. SS, which is the stack segment register. And the SSP, which is the shadow stack pointer register. And we have TPR, which is the task priority register. CR8, a new register introduced into the AMD64 architecture to speed interrupt management. And finally, we have TR, which is the task register. Then we have the Endian order. Okay. The x86 and AMD 64-bit architectures address memory using little endian byte ordering. Multi-byte values are stored with their least... Multi-byte values are stored with their least significant byte at the lowest byte address, and they are illustrated with their least significant byte at the right side. Strings are illustrated in reverse order because the address of their bytes increases from right to left. Ouch. Oh, this is hurting my brain. Indian order. I think this is something that Intel did, but it looks like AMD did it as well, or the x86 architecture did it. So it might be Intel x86 if Intel did do the x86 architecture. Okay, and then we have... Alright, so we have some books to look at. This is interesting, interesting, interesting. We might be able to find something down here. Okay, just by looking at this, the 8086 assembly language programming and 80... Okay, well, these are different. Okay. Processor BIOS writer's guide. Okay, interesting. Pentium. So I think my first computer I ever owned had a Pentium processor in it. Okay. Of course, the things that jump out to me as the first one being provided was the IBM PC assembly language and programming. And the 8086 Architecture and Programming Volume 2. So these might be good reads, potentially. This one actually sounds pretty good, which is the assembly language programming. As well as this one down here. Ooh, McGraw-Hill. Great publisher. At least I find it to be, most case. Liked, not. Oh, and it continues. Which is not a bad thing. That's a good thing. More books, the better. This is an interesting title. The Undocumented PC. Okay, we have the Institute of Electrical and Electronic Engineers, the IEEE standard for binary floating point arithmetic. So we have the standard here and here. This one seems nice. An assembly language introduction to computer architecture. Okay. Using the Intel Pentium. Actually, give me a second. I think it's sitting right here. I got the AMD K6. Flip this guy over. We have the Intel Pentium 5P100. So I got the Pentium processor right here in my hand. I don't have the motherboard or the computer to run it, but I have the CPU, and it was working order before I tore the computer apart like an idiot instead of saving it. And it saved me space, and I didn't have to move with it, so I don't know, saved me some time. Okay. Oh, this is cool. SIMD extensions in the Pentium 3. So SIMD was a part in the Pentium processor architecture. Okay. And we have websites and news groups. AMD.com, which is... And news of Microsoft. Okay. So that concludes the... What did we finish? The preface. Well, we finished the preface. It only took us an hour and some change. Not bad. I'll stop it here. And we'll continue this on later. Potentially. With the overview of the AMD 64-bit. Keep adding the bit. The AMD 64 architecture.
Thank you for watching. Hopefully you found this at least somewhat helpful.